After the defeat in the Japan-US War, rapid economic growth and a surge in transportation demand heightened expectations for electric railways capable of high-speed, high-capacity transportation. Electric multiple units, EMUs, which were considered unsuitable for premium trains due to noise and vibration, had the irreplaceable characteristics of being lightweight and high-powered, leading to technological improvements. The Japanese National Railways developed the 80 series EMUs, paving the way for EMUs to enter the premium train market. On the other hand, Odakyu Electric Railway, which had become independent from Tokyu Corporation, set an ambitious goal to reduce the travel time between Shinjuku and Odawara from approximately 100 minutes to 60 minutes. They actively pursued the development of high-performance electric multiple units, EMUs, to minimize the need for extensive investments in infrastructure improvements such as tracks and substations. They decided to develop lightweight, low center of gravity vehicles that would cause minimal track damage. This led to the decision to develop the DIHA 3000 series, known for its lightweight and low center of gravity design, which minimized track damage. The development was so significant that the Railway Technical Research Institute of the Japanese National Railways, JNR, also participated. The institute itself had become a re-employment destination for former naval aviation engineers, leading to the extensive incorporation of aircraft design concepts. Prioritizing weight reduction over future downgrading to general train operations, the focus was on body strength based on full passenger load. The car body adopted monocoque and honeycomb structures, trimming structural components that did not affect strength, achieving a 25% weight reduction compared to conventional designs. By reducing the vehicle weight, known as dead weight, which does not contribute to profitability, economic efficiency was improved. The average axle load in a loaded state was about 9.3 tons, approaching the value of the latest lightweight passenger car, the Naha 10, at that time. This was an astonishing lightness for an EMU carrying heavy electrical equipment. Emphasizing the image of being as light as a feather, it was initially called the feather train and attracted attention upon its debut. The leading car's streamlined shape was determined through wind tunnel experiments, and the sides of the car body were inclined inward by 4 degrees towards the roof to reduce the impact of crosswinds. The drive system adopted the cardan drive method, which was beginning to be put into practical use at that time. By lowering the floor outside the bogie area, a low center of gravity was achieved, with the passenger compartment floor height at 875 mm, lower than the 920 mm of the Kiha 391, which used small diameter wheels. In addition to high-speed stability, the articulated system, which was advantageous for weight reduction and had no ride comfort issues at the articulation section when passing curves, was adopted. The configuration consisted of 8 car bodies and 9 bogies. Of the 9 bogies, 6 were motorized bogies, and the entire train set had a weight of 147 tons and an output of 1,200 kilowatts. To enhance safety during high-speed operations, disc brakes were adopted for the first time on the trailer bogies. The headlights were equipped with shield beams that could switch between high and low beams, and the horn included a musical horn. The SE train, developed with the participation of the Railway Technical Research Institute of the Japanese National Railways, JNR, made a grand debut. Naturally, speed trials were conducted to verify its performance. Tests were conducted on the Odakyu line up to 127 km per hour, and further speed trials were attempted on the straighter Takeido main line. In 1957, it recorded 143 km per hour between Ofuna and Hiratsuka, and the next day, it broke the record with 145 km per hour. The tests were conducted with many observers on board, allowing them to experience the performance of the new generation of electric multiple units, EMUs. This speed became the world record for narrow-gauge railways at the time, and the technology developed through this project later evolved into the Kodama-type trains, and eventually the Shinkansen.